Imagine blasting off from Earth, not in the slow, plodding pace of today's chemical rockets, but with the raw, unbridled power of a star in your engine. That's the promise of nuclear thermal propulsion, a technology that could slash travel times to Mars in half and make deep space travel a reality. Picture this. Instead of spending months cooped up in a cramped spacecraft, you could be sipping your morning coffee while watching the red dust of Mars grow closer through your window. But how does it work? And is it safe? Stick around, because we're about to dive into the fiery heart of nuclear propulsion and explore why it might just be the future of deep space travel. The dawn of a new era in space travel. Nuclear thermal rockets, NTRs, represent a significant leap forward in propulsion technology, promising to revolutionize deep space travel. At their core, NTRs use a nuclear reactor to heat a propellant, typically hydrogen, to extremely high temperatures. This heated propellant is then expelled through a nozzle, generating thrust. The efficiency of this process is far superior to chemical rockets, which rely on the combustion of fuel and oxidizer. In an NTR, the nuclear reactor provides a consistent and powerful heat source, enabling higher exhaust velocities and thus greater fuel efficiency. The speed advantages of NTRs are staggering. For instance, a mission to Mars using conventional chemical rockets takes about 7 months. In contrast, an NTR-powered spacecraft could potentially reduce this travel time to just 3 months. This dramatic reduction in travel time isn't just about convenience. It's a game-changer for crewed missions. Longer journeys expose astronauts to more cosmic radiation and the psychological challenges of extended isolation. Shorter travel times mitigate these risks, making deep space exploration safer and more feasible. Safety is a paramount concern with any nuclear technology, and NTRs are no exception. The reactors used in NTRs are designed with multiple fail-safes to prevent accidents. Additionally, the propellant, often hydrogen, is stored and handled in ways that minimize risks. The high exhaust velocity of NTRs also means that less propellant is needed for a given mission, reducing the overall mass and complexity of the spacecraft. This not only improves safety, but also lowers the cost and logistical challenges of deep space travel. Moreover, the versatility of NTRs makes them suitable for a wide range of missions. Whether it's a crewed mission to Mars, a robotic exploration of the outer planets, or even a rapid response mission to an asteroid, NTRs offer a reliable and efficient propulsion solution. Their ability to operate independently of solar power makes them particularly valuable for missions far from the sun, where solar panels would be ineffective. In essence, NTRs are poised to open up new frontiers in space exploration, making the daunting distances of deep space more navigable and the dream of interplanetary travel more attainable. Current limitations of chemical propulsion. Chemical propulsion has been the backbone of space travel since its inception. It relies on the combustion of propellants to generate thrust. However, this method has significant limitations when it comes to deep space exploration. The fundamental issue lies in the energy density of chemical reactions. These reactions release a finite amount of energy, which translates into a limited exhaust velocity. For instance, the specific impulse, a measure of how effectively a rocket uses propellant, of chemical rockets typically tops out around 450 seconds. This means that while chemical propulsion is excellent for launching payloads into low Earth orbit, it falls short for missions requiring high delta-V, such as trips to Mars or beyond. Nuclear thermal rockets, NTRs, offer a compelling alternative. They operate by using a nuclear reactor to heat a propellant, usually hydrogen, to extremely high temperatures before expelling it through a nozzle. This process can achieve specific impulses of up to 900 seconds, more than double that of chemical rockets. The mechanics are straightforward yet powerful. A nuclear reactor heats the propellant, which expands and is forced out the back of the rocket, generating thrust. This higher exhaust velocity translates into faster travel times. For example, a mission to Mars using NTRs could take as little as 3 months, compared to the 6 to 9 months required by chemical rockets. This reduction in travel time is not just about convenience. It also significantly reduces the exposure of astronauts to cosmic radiation and the physiological effects of prolonged weightlessness. Safety is a critical consideration for any space travel technology. Nuclear thermal rockets have faced scrutiny due to the inherent risks associated with nuclear materials. However, modern designs incorporate fail-safes and redundant systems to minimize these risks. The reactor is only activated once the spacecraft has reached a safe distance from Earth, reducing the chance of accidental radiation exposure. Additionally, the use of low-enriched uranium further mitigates proliferation concerns. Despite these precautions, public perception and regulatory hurdles remain significant challenges. Yet, the potential benefits in terms of speed and efficiency make NTRs a promising avenue for future exploration. The ability to reach destinations faster not only reduces mission risks, but also opens up new possibilities for scientific discovery and human exploration. The need for advanced propulsion systems. Deep space travel presents unique challenges that current chemical propulsion systems struggle to overcome. The vast distances involved demand more efficient and powerful propulsion technologies. Chemical rockets, while effective for reaching low Earth orbit and even the Moon, fall short when considering missions to Mars and beyond. Their limited specific impulse, a measure of how effectively a rocket uses propellant, means they require enormous amounts of fuel, making long-distance missions impractical. For instance, a journey to Mars using chemical propulsion can take between 6 to 9 months, a duration that poses significant risks to astronauts' health and mission success. Nuclear thermal rockets, NTRs, offer a promising alternative. These systems use a nuclear reactor to heat a propellant, typically hydrogen, to extremely high temperatures before expelling it through a nozzle to generate thrust. This process achieves a higher specific impulse than chemical rockets, resulting in greater fuel efficiency and faster travel times. For example, an NTR could potentially reduce the travel time to Mars to around 3 months, significantly cutting the exposure of astronauts to cosmic radiation and the physiological effects of prolonged space travel. The mechanics behind NTRs are relatively straightforward. A fission reactor heats the propellant, which expands and is ejected at high velocity, producing thrust. This efficiency makes NTRs particularly suitable for deep space missions where fuel weight is a critical factor. Safety is a paramount concern with nuclear propulsion. However, advancements in reactor design and shielding technologies have mitigated many of the risks associated with nuclear materials in space. Modern NTRs are designed with fail-safes to prevent accidental radiation release, and the use of low-enriched uranium further reduces proliferation concerns. Additionally, the reactor is only activated once the spacecraft has reached a safe distance from Earth, minimizing the risk to the planet. The speed and efficiency of NTRs not only make deep space travel more feasible, but also open up new possibilities for exploration. Faster travel times mean that missions can be completed more quickly, reducing the overall risk and cost. This could enable more frequent and ambitious missions to the outer planets and even interstellar probes, pushing the boundaries of human exploration. Understanding nuclear propulsion. Nuclear propulsion stands out as a promising technology for deep space travel, offering significant advantages over conventional chemical rockets. At its core, nuclear thermal propulsion, NTP, involves using a nuclear reactor to heat a propellant, typically hydrogen, to extremely high temperatures. This heated propellant is then expelled through a nozzle to generate thrust. The process leverages the immense energy released during nuclear fission, which is far more efficient than the chemical reactions used in traditional rockets. This efficiency translates into higher exhaust velocities and, consequently, greater fuel efficiency. In practical terms, NTP systems can achieve specific impulses, a measure of how effectively a rocket uses propellant, 2 to 3 times higher than chemical rockets. For instance, while chemical rockets might achieve a specific impulse of around 450 seconds, NTP systems can reach values exceeding 900 seconds. This means that for the same amount of propellant, a nuclear thermal rocket can generate more thrust over a longer period. The result is a dramatic reduction in travel time. A mission to Mars, which might take 6 to 9 months with chemical rockets, could be cut down to about 3 months with NTP. This reduction in travel time not only makes deep space missions more feasible, but also significantly reduces the risks associated with prolonged exposure to space radiation and microgravity. Safety is a critical consideration for any space technology, and nuclear propulsion is no exception. The design of NTP systems includes multiple fail-safes to prevent accidental nuclear reactions. Reactors are typically shielded and designed to operate only under specific conditions, minimizing the risk of unintended activation. Additionally, the use of low-enriched uranium further reduces the potential for proliferation concerns. Despite these safeguards, the idea of launching a nuclear-powered rocket can be unsettling. However, the benefits in terms of speed and efficiency make it a compelling option for future space exploration. The ability to reach destinations faster and with more payload capacity could revolutionize our approach to interplanetary travel, making it more accessible and sustainable. Moreover, the speed advantages of NTP extend beyond just reaching destinations quicker. Faster travel times also mean that missions can be completed more efficiently, reducing the overall cost and complexity. For example, a quicker trip to Mars would require less supplies, as the crew would spend less time in transit. This reduction in resource requirements can make missions more feasible and cost-effective. The potential for NTP to enable faster, more efficient space travel makes it a key technology for the future of deep space exploration. As we look to expand our presence beyond Earth, the advantages of nuclear propulsion become increasingly apparent, offering a pathway to more ambitious and far-reaching missions. Types of nuclear propulsion, NERVA, and beyond. Nuclear thermal rockets, NTRs, represent a significant leap forward in propulsion technology, offering a more efficient and powerful alternative to traditional chemical rockets. At their core, NTRs use a nuclear reactor to heat a propellant, typically hydrogen, to extremely high temperatures before expelling it through a nozzle to generate thrust. This process leverages the immense energy released by nuclear fission, which is far greater than the energy from chemical reactions used in conventional rockets. The heated propellant expands rapidly, creating a high-velocity exhaust that propels the spacecraft forward. This method not only increases the specific impulse, the measure of how effectively a rocket uses propellant, but also significantly reduces the amount of fuel required for a given mission. One of the most notable examples of nuclear thermal propulsion is the nuclear engine for rocket vehicle application, NERVA. NERVA utilized a solid-core nuclear reactor to heat hydrogen, achieving a specific impulse roughly twice that of the most advanced chemical rockets. This translates to faster travel times and greater payload capacities. For instance, a mission to Mars using NERVA technology could potentially cut travel time from the typical 6 to 9 months with chemical rockets to just a few months. The reduced travel time not only minimizes the exposure of astronauts to cosmic radiation, but also decreases the overall mission risk and resource requirements. The efficiency of NERVA's design highlights the potential of nuclear thermal propulsion to revolutionize deep space travel. Safety is a critical consideration in the development and deployment of nuclear thermal rockets. The use of nuclear materials inherently raises concerns about radiation exposure and the potential for accidents. However, modern designs incorporate robust safety features, such as fail-safe mechanisms and redundant systems, to mitigate these risks. For example, reactors can be designed to automatically shut down in the event of an anomaly, and shielding can be used to protect both the crew and the environment from radiation. Additionally, the high specific impulse of NTRs means that less fuel is needed, reducing the overall mass and complexity of the spacecraft. This not only enhances safety, but also improves the reliability and efficiency of the mission. Beyond NERVA, advancements in nuclear thermal propulsion continue to push the boundaries of what is possible. Researchers are exploring new reactor designs, such as gas core and fission fragment rockets, which promise even higher specific impulses and greater efficiency. These next-generation technologies could enable missions to the outer planets and beyond, opening up new possibilities for exploration and scientific discovery. The speed and efficiency of nuclear thermal propulsion make it a compelling option for future deep space missions, offering a viable path to the stars. As technology advances, the potential for nuclear propulsion to transform space travel becomes increasingly apparent, heralding a new era of exploration and innovation. The science behind nuclear thermal propulsion. Nuclear thermal propulsion, NTP, harnesses the immense energy released during nuclear fission to heat a propellant, typically hydrogen, to extreme temperatures. This heated propellant is then expelled through a nozzle at high speeds, generating thrust. The process begins with a fission reactor, which uses uranium or another fissile material to produce heat. This heat is transferred to a propellant, usually liquid hydrogen, which is stored in a tank. The hydrogen is then pumped into the reactor core, where it is heated to temperatures exceeding 500 degrees Celsius. The superheated hydrogen gas expands and is expelled through a nozzle, creating thrust. This method is significantly more efficient than chemical rockets because it leverages the high energy density of nuclear reactions. In contrast to chemical rockets, which rely on the combustion of fuel and oxidizer, NTP systems offer a substantial advantage in terms of specific impulse, a measure of how effectively a rocket uses propellant. Chemical rockets typically achieve a specific impulse of around 450 seconds, while NTP systems can reach specific impulses of up to 900 seconds. This means that NTP rockets can generate more thrust per unit of propellant, resulting in faster travel times and greater efficiency. For example, a mission to Mars using chemical propulsion might take around 7 months, whereas an NTP-powered spacecraft could potentially reduce this travel time to just a few months. This reduction in travel time is not only beneficial for crewed missions, but also for robotic explorers, as it minimizes exposure to cosmic radiation and other hazards of deep space travel. Safety is a critical consideration in the development of NTP systems. The use of nuclear materials inherently raises concerns about radiation exposure and the potential for accidents. However, modern NTP designs incorporate several safety features to mitigate these risks. For instance, the reactor core is typically shielded to contain radiation, and the propellant is stored separately from the reactor to prevent contamination. Additionally, NTP systems can be designed to operate at lower power levels during critical phases of the mission, such as launch and reentry, to minimize the risk of accidental radiation release. Despite these precautions, the safety of NTP systems remains a topic of ongoing research and debate. Advocates argue that the benefits of faster, more efficient space travel outweigh the risks, while critics emphasize the need for rigorous safety protocols and further testing. The speed advantages of NTP are particularly compelling for deep space missions. The ability to achieve higher specific impulse translates into faster acceleration and higher top speeds. This is crucial for missions to the outer planets and beyond, where the distances are vast and travel times can be measured in years. For example, a mission to Jupiter using chemical propulsion might take several years, whereas an NTP-powered spacecraft could potentially make the journey in a fraction of that time. This speed advantage not only reduces the overall mission duration, but also allows for more flexible mission planning and the possibility of multiple flybys or rendezvous with different celestial bodies. The faster travel times also mean that spacecraft can spend more time conducting scientific observations and less time in transit, enhancing the overall productivity of the mission. Advantages of nuclear propulsion over chemical rockets. Nuclear thermal rockets, NTRs, operate on a principle that's strikingly different from chemical rockets. They use a nuclear reactor to heat a propellant, typically hydrogen, to extremely high temperatures before expelling it through a nozzle to generate thrust. This process is more efficient than chemical combustion, which relies on the energy released from propellant reactions. The high temperatures and exhaust velocities achieved in NTRs result in a specific impulse, a measure of fuel efficiency, that's significantly higher than that of chemical rockets. For instance, while the best chemical rockets achieve a specific impulse of around 450 seconds, NTRs can reach values exceeding 900 seconds. This means that nuclear thermal rockets can go farther and faster with the same amount of fuel. The most striking advantage of nuclear propulsion is the dramatic reduction in travel time to distant destinations. Take Mars, for example. A typical chemical rocket mission to the Red Planet takes about 7 months. In contrast, a nuclear thermal rocket could cut that journey down to just 3 or 4 months. This isn't just about convenience. Shorter travel times reduce the risks associated with prolonged space exposure, such as radiation and the physical and psychological toll on astronauts. Moreover, faster trips mean more launch opportunities and greater flexibility in mission planning. The ability to reach destinations quickly and efficiently opens up new possibilities for deep space exploration, making it easier to resupply stations or evacuate crews in emergencies. Safety is often a contentious topic when discussing nuclear technology. However, modern NTR designs incorporate several fail-safes to minimize risks. The reactors are designed to operate only after the spacecraft has reached a safe distance from Earth, reducing the chance of accidental radiation exposure. Additionally, the use of low-enriched uranium and passive safety features ensures that the reactor can't melt down or explode. In fact, the probability of a catastrophic failure is extremely low. Furthermore, the speed advantage of nuclear propulsion isn't just about getting there faster. It's also about reducing the time spent in the harsh environment of space. Faster trips mean less exposure to cosmic radiation and microgravity, which can have detrimental effects on human health. By cutting travel times, nuclear propulsion effectively makes deep space travel safer for astronauts. Nuclear propulsion and the future of Mars missions. Nuclear thermal rockets, NTRs, represent a significant leap forward in space propulsion technology. These engines use a nuclear reactor to heat a propellant, typically hydrogen, to extremely high temperatures. The heated propellant is then expelled through a nozzle to generate thrust. This process is far more efficient than chemical rockets, which rely on the combustion of fuel and oxidizer. The high energy density of nuclear reactions allows NTRs to achieve specific impulses, a measure of fuel efficiency, up to 3 times greater than the best chemical rockets. This translates to faster travel times and the ability to carry more payload, making them ideal for long-distance space missions. The speed advantage of nuclear thermal rockets is particularly evident when comparing travel times to Mars. Chemical rockets, which are currently used for space travel, take about 7 months to reach Mars when the planets are favorably aligned. In contrast, NTRs could potentially cut this travel time in half, reducing the journey to around 3 to 4 months. Shorter travel times are not just about convenience. They also reduce the exposure of astronauts to harmful space radiation and the psychological strain of long-duration spaceflight. Additionally, faster trips mean that missions can take advantage of shorter launch windows, increasing the flexibility and frequency of Mars missions. Safety is a critical consideration for any space mission, and nuclear thermal rockets are designed with multiple safeguards to ensure the protection of both the crew and the environment. The nuclear reactor is only activated once the spacecraft has reached a safe distance from Earth, minimizing the risk of accidental radiation exposure. Furthermore, the reactor is shielded to contain radiation, and the design includes fail-safes to prevent meltdowns. While the idea of using nuclear power in space might seem daunting, the technology has been extensively tested and refined. Ground tests, such as those conducted during the NERVA, Nuclear Engine for Rocket Vehicle Application, program, have demonstrated the feasibility and safety of NTRs. The potential benefits in terms of speed, efficiency, and payload capacity make nuclear thermal rockets a promising technology for the future of Mars missions, enabling faster travel to the outer planets. Nuclear thermal rockets, NTRs, represent a significant leap forward in propulsion technology, offering a more efficient and powerful alternative to traditional chemical rockets. At their core, NTRs use a nuclear reactor to heat a propellant, typically hydrogen, to extremely high temperatures before expelling it through a nozzle to generate thrust. This process leverages the principles of thermodynamics and fluid dynamics to achieve higher specific impulse, a measure of how effectively a rocket uses propellant compared to chemical rockets. The result is a propulsion system that can deliver more thrust for less fuel, making it ideal for long-distance space travel. The primary advantage of NTRs over chemical rockets is their ability to drastically reduce travel times to the outer planets. For instance, a mission to Mars using a chemical rocket might take around 7 months, but an NTR could potentially cut that time in half. This reduction in travel time is not just a matter of convenience. It has profound implications for crew health, mission logistics, and overall feasibility. Shorter travel times mean less exposure to cosmic radiation, reduced psychological stress for astronauts, and lower consumable requirements, such as food and water. These factors collectively make NTRs a more viable option for deep space exploration. Safety is a critical consideration when discussing nuclear propulsion. While the idea of using nuclear reactors in space might seem daunting, extensive research and development have shown that NTRs can be designed with robust safety features. The reactors used in NTRs are typically shielded to prevent radiation leakage, and the propellant itself acts as a cooling mechanism, reducing the risk of overheating. Additionally, the use of low-enriched uranium further minimizes the potential for nuclear proliferation concerns. These safety measures, combined with rigorous testing protocols, ensure that NTRs can be operated safely and reliably in the harsh environment of space. The speed advantages of NTRs are not limited to theoretical scenarios. Real-world testing and simulations have demonstrated their potential to revolutionize space travel. For example, a nuclear thermal rocket could enable a mission to Jupiter in just over 2 years, compared to the 5 to 6 years it would take a chemical rocket. This speed not only makes exploration more efficient, but also opens up new possibilities for scientific discovery. Faster travel times allow for more frequent missions, increased data collection, and the potential for real-time communication with Earth. These benefits make NTRs a compelling option for the future of deep space exploration. Nuclear propulsion for manned missions to Europa. Nuclear thermal rockets, NTRs, offer a promising solution for manned missions to Europa, one of Jupiter's moons, due to their superior efficiency and speed compared to conventional chemical rockets. At their core, NTRs use a nuclear reactor to heat a propellant, typically hydrogen, to extremely high temperatures. This heated propellant is then expelled through a nozzle, generating thrust. The key advantage lies in the reactor's ability to reach temperatures far beyond what chemical reactions can achieve, resulting in a higher exhaust velocity and thus greater fuel efficiency. The mechanics of NTRs are relatively straightforward. A solid-fueled nuclear reactor heats the propellant, which is stored in a separate tank. The heated propellant expands and is ejected at high speed, creating thrust. This process is more efficient than chemical rockets because it doesn't rely on the combustion of fuel and oxidizer. Instead, it uses the direct heat from nuclear fission, which can be controlled and sustained for longer periods. This allows for continuous thrust and higher specific impulse, a measure of how effectively a rocket uses propellant. When comparing travel times, the advantages of NTRs become evident. A chemical rocket might take around 6 years to reach Europa, depending on the alignment of Earth and Jupiter. In contrast, an NTR-powered spacecraft could potentially make the journey in half that time. This significant reduction in travel time is crucial for manned missions, as it minimizes the exposure of astronauts to cosmic radiation and the physiological effects of prolonged space travel. Faster travel times also mean that missions can be completed more quickly, reducing the overall risk and resource requirements. Safety is a paramount concern for any manned mission, and NTRs address this in several ways. The reactor is designed with multiple fail-safes to prevent accidental fission or overheating. Additionally, the propellant, usually hydrogen, is stored separately from the reactor, reducing the risk of contamination or explosion. The use of low-enriched uranium further mitigates the risk of nuclear proliferation. Despite these safety measures, the idea of a nuclear reactor in space might seem daunting. However, extensive ground testing and simulations have shown that NTRs can be operated safely and reliably. The potential benefits in terms of speed and efficiency make them a compelling choice for future deep space exploration. The role of nuclear propulsion in asteroid exploration. Nuclear thermal rockets, NTRs, operate on a principle that's deceptively simple yet profoundly effective. At their core, they use a nuclear reactor to heat a propellant, typically hydrogen, to extreme temperatures. This superheated gas is then expelled through a nozzle, generating thrust. The key advantage lies in the reactor's ability to reach temperatures far beyond what chemical rockets can achieve. Chemical rockets rely on combustion, which is limited by the energy stored in the fuel's molecular bonds. In contrast, nuclear reactors can sustain much higher temperatures, leading to significantly higher exhaust velocities. This translates to greater efficiency and, crucially, faster travel times. Consider a mission to a near-Earth asteroid, like Bennu or Ryugu. With conventional chemical rockets, such a journey could take months. The exact duration depends on the asteroid's orbit and the alignment of Earth and the target. However, nuclear thermal rockets could cut this time substantially. For instance, an NTR-powered spacecraft might reach Bennu in a fraction of the time it takes a chemical rocket. This speed isn't just about convenience. It's about reducing the exposure of astronauts to cosmic radiation and microgravity, both of which pose significant health risks. Faster travel times also mean that missions can be completed more quickly, reducing the logistical challenges and costs associated with long-duration spaceflight. Safety is, of course, a paramount concern when discussing nuclear technology in space. The reactors used in NTRs are designed with multiple fail-safes to prevent accidents. Moreover, the reactors are only activated once the spacecraft has reached a safe distance from Earth. This minimizes the risk of radioactive contamination in case of a launch or ascent failure. Additionally, the use of low-enriched uranium further reduces proliferation concerns. Despite these safeguards, public perception remains a hurdle. However, the potential benefits, faster travel times, increased payload capacity, and the ability to explore more distant destinations make NTRs a compelling option for future asteroid exploration missions. The speed and efficiency of nuclear thermal rockets open up new possibilities for scientific research. Asteroids are remnants from the early solar system, and studying them can provide invaluable insights into planetary formation and the origins of life. With faster travel times, scientists can conduct more detailed and extensive studies. They can also reach multiple asteroids in a single mission, something that's currently impractical with chemical rockets. This could revolutionize our understanding of these celestial bodies and their potential resources. For example, some asteroids are rich in water and precious metals, which could be harvested for use in space or brought back to Earth. The faster we can get there, the sooner we can start unlocking these resources. Nuclear propulsion and the search for extraterrestrial life. Nuclear thermal rockets, NTRs, represent a significant leap forward in space propulsion technology. They operate by using a nuclear reactor to heat a propellant, typically hydrogen, to extremely high temperatures. This heated propellant is then expelled through a nozzle to generate thrust. The efficiency of NTRs stems from their ability to achieve higher specific impulse compared to chemical rockets. Specific impulse is a measure of how effectively a rocket uses propellant, and higher values translate to more efficient fuel usage and greater speeds. For instance, while chemical rockets might achieve a specific impulse of around 450 seconds, NTRs can reach values exceeding 900 seconds. This means that for the same amount of propellant, an NTR can provide nearly twice the thrust over a longer period, making it ideal for long-duration space missions. The speed and efficiency of nuclear thermal rockets offer a stark contrast to traditional chemical rockets. Chemical rockets, which rely on the combustion of fuel and oxidizer, are limited by the energy density of their propellants. This limitation results in longer travel times, especially for deep space missions. For example, a mission to Mars using chemical propulsion might take around 7 months. In contrast, an NTR-powered spacecraft could potentially reduce this travel time to just a few months. This reduction in travel time is not only beneficial for the crew's well-being, but also for the mission's overall success. Faster travel times mean less exposure to cosmic radiation and microgravity, which can have detrimental effects on human health. Additionally, shorter missions require less supplies, reducing the overall mass and complexity of the spacecraft. Safety is a critical consideration in the development and deployment of nuclear thermal rockets. The use of nuclear materials inherently raises concerns about radiation exposure and potential accidents. However, modern NTR designs incorporate multiple safety features to mitigate these risks. For instance, reactors are designed to operate at lower power levels during launch and ascent, minimizing the risk of a nuclear incident. Additionally, the use of fail-safe mechanisms and redundant systems ensures that any potential issues can be quickly addressed. The propellant itself, usually hydrogen, is also chosen for its low toxicity and ease of handling. Despite these precautions, the public and regulatory bodies often express concerns about the safety of nuclear propulsion. Addressing these concerns requires transparent communication and rigorous testing to demonstrate the reliability and safety of NTR technology. As research and development continue, the balance between the benefits of faster, more efficient space travel and the need for safety will be carefully managed to ensure the successful implementation of nuclear thermal rockets in future missions. Overcoming the challenges of nuclear propulsion. Nuclear thermal rockets, NTRs, operate on a principle that's deceptively simple. Heat a propellant, like hydrogen, to extreme temperatures using a nuclear reactor and then expel it through a nozzle to generate thrust. This process is far more efficient than chemical rockets. Chemical rockets carry both fuel and oxidizer, which, when combined, create a hot gas that's expelled to produce thrust. However, the energy released is limited by the chemical bonds in the propellant. In contrast, NTRs use nuclear fission to heat the propellant, releasing vastly more energy. This allows NTRs to achieve higher exhaust velocities, resulting in greater fuel efficiency and faster travel times. Consider a mission to Mars. A chemical rocket might take around 7 months to reach the red planet. An NTR, with its higher exhaust velocity, could cut that travel time significantly. The reduced transit time isn't just about convenience. It's a critical safety factor. Longer missions expose astronauts to more cosmic radiation and increase the risk of system failures. Faster travel times mitigate these risks, making deep space exploration safer. Safety is a paramount concern with nuclear propulsion. The idea of launching a nuclear reactor into space might sound alarming, but extensive safeguards are in place. Reactors for NTRs are designed to withstand the rigors of launch and space travel. They use low-enriched uranium, reducing the risk of nuclear proliferation. Moreover, the reactor is only activated once the spacecraft has reached a safe distance from Earth. In the event of an accident during launch, the reactor's design ensures that it remains subcritical, preventing a nuclear meltdown. Extensive testing and simulation are conducted to address potential failure scenarios, ensuring that nuclear propulsion is as safe as possible. Speed is another significant advantage of nuclear propulsion. The higher exhaust velocities of NTRs translate into faster travel times, opening up the possibility of crewed missions to the outer planets. For instance, a mission to Jupiter using chemical propulsion would take years. With NTRs, that travel time could be reduced to a matter of months. This speed is not just about getting there faster. It's about expanding the boundaries of human exploration. Faster travel times mean that more missions can be conducted in the same time frame, accelerating our understanding of the solar system. Additionally, the increased speed allows for more flexible mission planning, as spacecraft can adjust their trajectories more easily to account for unexpected events. Safety concerns and public perception. Nuclear thermal rockets, NTRs, operate by using a nuclear reactor to heat a propellant, typically hydrogen, to extreme temperatures. This heated propellant is then expelled through a nozzle to generate thrust. The process is more efficient than chemical rockets because it achieves higher exhaust velocities. In a chemical rocket, the energy is produced by the combustion of fuel and oxidizer, which is then expelled to create thrust. The specific impulse, a measure of how effectively a rocket uses propellant, is significantly higher in NTRs. For instance, while chemical rockets might achieve a specific impulse of around 450 seconds, NTRs can reach up to 900 seconds. This means that for the same amount of propellant, an NTR can provide nearly double the thrust. The increased efficiency of NTRs translates to shorter travel times for deep space missions. A mission to Mars, which might take around 7 months with current chemical rocket technology, could be reduced to about 3 months with NTRs. This reduction in travel time is not just about convenience. It has significant implications for crew health and mission logistics. Longer missions expose astronauts to more radiation and the psychological stresses of extended confinement. Shorter travel times also reduce the amount of supplies needed, making the mission more feasible and less costly. However, the use of nuclear propulsion raises safety concerns. The primary worry is the risk of a launch accident that could release radioactive material. To mitigate this, NTRs are designed with multiple safety features, including fail-safe mechanisms that prevent the reactor from reaching criticality during a launch failure. Additionally, The reactors are often designed to be inherently safe, meaning that they cannot sustain a chain reaction without active cooling. Public perception is another hurdle. The term nuclear often evokes fear and resistance, largely due to historical incidents and the association with nuclear weapons. Education and transparent communication about the safety measures and benefits of nuclear propulsion are crucial to shifting public opinion. Demonstrating the reliability and safety of NTRs through successful missions and rigorous testing can help build trust and acceptance. Nuclear propulsion and international space law. Nuclear thermal rockets, NTRs, operate by heating a propellant, typically hydrogen, to extremely high temperatures using a nuclear reactor. This heated propellant is then expelled through a nozzle to generate thrust. The process is more efficient than chemical rockets because nuclear reactions release far more energy per unit of mass compared to chemical reactions. In an NTR, the reactor's heat converts the hydrogen into a plasma, which is expelled at high velocities. This results in a specific impulse, a measure of how effectively a rocket uses propellant, that is significantly higher than that of chemical rockets. For instance, while chemical rockets achieve specific impulses around 450 seconds, NTRs can reach up to 900 seconds. This means NTRs can travel faster and farther using the same amount of propellant. The speed advantage of NTRs over chemical rockets is substantial. A mission to Mars, for example, could take roughly 4 to 6 months using chemical propulsion. With NTRs, this travel time could be cut in half. The reduced travel time not only makes deep space missions more feasible, but also minimizes the exposure of astronauts to cosmic radiation and the physiological effects of prolonged space travel. Additionally, faster travel times reduce the amount of supplies needed, as the spacecraft would spend less time in transit. This efficiency could be a game-changer for missions to the outer planets and beyond. Safety is a critical consideration for nuclear propulsion. The primary concern is the risk of a nuclear accident during launch or re-entry. To mitigate this, NTRs are designed with multiple fail-safes and redundant systems. The reactor is only activated once the spacecraft has reached a safe distance from Earth. Moreover, the use of low-enriched uranium and passive safety features helps to minimize the risk of a nuclear meltdown. International space law, particularly the Outer Space Treaty of 1967, addresses the use of nuclear power in space. The treaty prohibits the placement of nuclear weapons or other weapons of mass destruction in orbit around the Earth, in installations on the Moon, or on any other celestial body. However, it does not explicitly ban the use of nuclear propulsion for peaceful purposes. This legal framework ensures that nuclear propulsion can be pursued responsibly, with a focus on safety and the prevention of harmful contamination. International space law also plays a role in the regulation of nuclear propulsion. The liability conventions, for example, establish procedures for dealing with damage caused by space objects, including those powered by nuclear propulsion. These conventions ensure that countries and organizations are held accountable for any damage caused by their space activities. Additionally, the principles of environmental protection in space, as outlined in various international agreements, emphasize the need to avoid harmful contamination of the space environment. This includes the responsible use of nuclear propulsion to prevent radioactive materials from contaminating celestial bodies or the Earth's atmosphere. By adhering to these legal frameworks, the use of nuclear propulsion can be conducted in a manner that is both safe and sustainable. The economic viability of nuclear propulsion. Nuclear thermal rockets, NTRs, operate by using a nuclear reactor to heat a propellant, typically hydrogen, to extremely high temperatures before expelling it through a nozzle to generate thrust. This process is fundamentally different from chemical rockets, which rely on the combustion of fuel and oxidizer. The high energy density of nuclear reactions allows NTRs to achieve significantly higher specific impulse, a measure of fuel efficiency, compared to chemical rockets. For instance, while chemical rockets might achieve a specific impulse of around 450 seconds, NTRs can reach values exceeding 900 seconds. This translates to faster travel times and greater payload capacities, making them highly attractive for deep space missions. Contrasting travel times, a mission to Mars using chemical propulsion might take around 7 months. In contrast, an NTR-powered spacecraft could potentially reduce this travel time to as little as 3 months. This dramatic reduction in travel time not only decreases the exposure of astronauts to harmful space radiation, but also lowers the overall mission risk and resource requirements. Faster travel times also enable more frequent missions and greater flexibility in mission planning. For example, shorter travel times could allow for more frequent resupply missions to a Mars colony, enhancing its sustainability and growth. Safety is a critical consideration for any space technology, and NTRs are designed with multiple fail-safes to ensure operational safety. The nuclear reactor is typically shielded and designed to operate at lower power levels during critical phases of the mission, such as launch and reentry. Additionally, the use of low-enriched uranium reduces the risk of nuclear proliferation. Despite these safeguards, public perception and regulatory hurdles remain significant challenges. However, the potential benefits of NTRs in terms of speed and efficiency make them a compelling option for future deep space exploration. The economic viability of NTRs is further enhanced by their ability to carry heavier payloads, which can include scientific equipment, supplies, and even human habitats, making them a cost-effective solution for long-term space missions. Comparing nuclear propulsion with other advanced technologies. Nuclear thermal rockets, NTRs, operate by heating a propellant, typically hydrogen, to extreme temperatures using a nuclear fission reactor. This heated propellant is then expelled through a nozzle to generate thrust. The high energy density of nuclear reactions allows NTRs to achieve exhaust velocities significantly higher than those of chemical rockets. For instance, while chemical rockets might achieve exhaust velocities around 4.5 kilometers per second, NTRs can reach velocities upwards of 9 kilometers per second. This substantial increase in exhaust velocity translates to shorter travel times for deep space missions. A mission to Mars, which might take around 7 months with conventional chemical propulsion, could potentially be reduced to about 3 months with NTRs. This reduction in travel time not only decreases the exposure of astronauts to cosmic radiation, but also lowers the overall mission risk and resource requirements. In contrast to nuclear thermal propulsion, other advanced technologies like electric propulsion systems, such as ion or Hall-effect thrusters, offer high specific impulse but at the cost of low thrust levels. These systems are well suited for long-duration missions where gradual acceleration is acceptable, such as satellite station keeping or slow trajectories to distant asteroids. However, their low thrust makes them impractical for rapid transits to destinations like Mars or the outer planets. Chemical rockets, while providing high thrust for quick launches, are limited by the energy density of their propellants, which results in lower exhaust velocities and longer travel times. Solar sails, another advanced technology, rely on the momentum transfer from photons to accelerate a spacecraft. While they offer the potential for continuous acceleration without propellant, their performance is heavily dependent on the intensity of solar radiation, which diminishes with distance from the Sun. This makes them less viable for missions beyond the asteroid belt. Safety is a critical consideration for any space propulsion technology. Nuclear thermal rockets present unique challenges due to the handling and storage of radioactive materials. However, advancements in reactor design and safety protocols aim to mitigate these risks. Modern NTR concepts incorporate fail-safe mechanisms to prevent accidental fission reactions and ensure that radioactive materials are contained even in the event of a malfunction. Additionally, the use of low-enriched uranium and advanced shielding materials helps to minimize radiation exposure to both the spacecraft and any potential planetary bodies it might encounter. In comparison, chemical rockets, while generally safer in terms of radiation, pose risks associated with the storage and handling of highly energetic propellants. Electric propulsion systems, on the other hand, are relatively safe in terms of both radiation and propellant hazards, but their low thrust levels can complicate mission profiles and increase the overall duration of the journey. The speed advantages of nuclear thermal propulsion are particularly evident when comparing it to other advanced technologies. For instance, a mission to Jupiter using chemical propulsion might take several years, whereas an NTR-equipped spacecraft could potentially make the journey in a fraction of that time. This speed is not just about reducing travel time. It also opens up new possibilities for exploration. Faster transit times allow for more flexible mission planning and the potential for multiple flybys or rendezvous with different celestial bodies. Moreover, the ability to carry out missions more quickly reduces the operational complexities and costs associated with long-duration space travel. While other advanced technologies like electric propulsion and solar sails have their own niche applications, the combination of high thrust and high specific impulse offered by NTRs makes them a compelling option for the future of deep space exploration. Nuclear Electric Propulsion, a complementary technology. Nuclear Electric Propulsion, NEP, offers a compelling alternative to traditional chemical rockets, particularly for long-duration space missions. Unlike chemical rockets, which rely on the combustion of propellants to generate thrust, NEP systems use a nuclear reactor to produce electricity. This electricity powers an ion drive or other electric propulsion system, which accelerates ions to high velocities. The result is a propulsion system that is more efficient and capable of sustained operation over extended periods. One of the primary advantages of NEP is its superior specific impulse, a measure of how effectively a propulsion system uses propellant. Chemical rockets typically have specific impulses ranging from 300 to 450 seconds, while NEP systems can achieve specific impulses of several thousand seconds. This means that NEP systems can provide continuous, low-thrust propulsion over long durations, making them ideal for deep space missions. For example, a mission to Mars using NEP could potentially reduce travel time compared to chemical rockets, depending on the mission profile and propulsion system design. Safety is a critical consideration for any space propulsion system, and NEP is no exception. The nuclear reactors used in NEP systems are designed with multiple layers of safety features to prevent accidents. These include passive cooling systems, fail-safe mechanisms, and robust shielding to protect both the spacecraft and any potential planetary bodies from contamination. Additionally, the use of low-enriched uranium or other safe nuclear fuels further mitigates risks. While the idea of nuclear propulsion might raise concerns, the technology has been extensively studied and tested, with a strong safety record in both terrestrial and space applications. Speed is another area where NEP shines. While chemical rockets provide high thrust for short durations, NEP systems offer a more gradual but sustained acceleration. This makes NEP particularly suitable for missions that require precise maneuvering and long-duration travel. For instance, a spacecraft equipped with NEP could potentially reach the outer planets more quickly than a chemical rocket, thanks to its higher specific impulse and continuous thrust. The trade-off is that NEP systems require more time to build up speed, but once they do, they can maintain that speed more efficiently over long distances. This makes them a valuable complement to other propulsion technologies, particularly for missions that demand both efficiency and endurance. Nuclear propulsion and the vision for interstellar travel. Nuclear thermal rockets, NTRs, represent a significant leap forward in space propulsion technology. These engines use a nuclear reactor to heat a propellant, typically hydrogen, to extremely high temperatures before expelling it through a nozzle to generate thrust. The process is remarkably efficient compared to conventional chemical rockets. In a chemical rocket, the energy is derived from the combustion of fuel and oxidizer, which limits the exhaust velocity and, consequently, the overall performance. Nuclear thermal rockets, on the other hand, achieve higher exhaust velocities by leveraging the intense heat from nuclear fission. This results in a specific impulse, a measure of fuel efficiency, that is roughly twice that of the most advanced chemical rockets. For instance, while the Space Shuttle's main engines had a specific impulse of around 450 seconds, NTRs can reach specific impulses of 800 to 1,000 seconds. The speed and efficiency of nuclear thermal rockets translate into significantly shorter travel times for deep space missions. A mission to Mars, which typically takes about 7 months with chemical propulsion, could be reduced to as little as 3 months using NTRs. This reduction in travel time not only decreases the exposure of astronauts to harmful cosmic radiation, but also minimizes the psychological and physiological effects of prolonged space travel. The faster transit times also open up the possibility of crewed missions to the outer planets, such as Jupiter and Saturn, which are currently beyond the reach of chemical rockets due to the extended duration and fuel requirements. For example, a journey to Jupiter with chemical propulsion would take several years, whereas NTRs could potentially cut this down to a few months. Safety is a critical consideration in the development and deployment of nuclear thermal rockets. The primary concern revolves around the handling and containment of radioactive materials during launch and operation. To mitigate these risks, NTRs are designed with robust shielding and fail-safe mechanisms to prevent accidental release of radiation. Additionally, the use of low-enriched uranium as fuel, as opposed to highly enriched uranium, reduces the proliferation risks associated with nuclear materials. Ground testing and extensive simulations are conducted to ensure the reliability and safety of these systems before they are deployed in space. The potential benefits of NTRs in terms of speed and efficiency far outweigh the risks, making them a promising technology for the future of deep space exploration. The path to commercializing nuclear propulsion. Nuclear thermal rockets, NTRs, operate on a principle that's deceptively simple yet profoundly effective. A fission reactor heats a propellant, typically hydrogen, to extremely high temperatures. This heated propellant is then expelled through a nozzle, generating thrust. The key advantage here is efficiency. Chemical rockets convert only a small percentage of their fuel's energy into thrust, while NTRs can harness a much larger portion, resulting in a specific impulse. Essentially, fuel efficiency, 2 to 3 times greater than chemical rockets. This translates to faster travel times and the ability to carry more payload, as less fuel is needed for the same journey. Consider a mission to Mars. A chemical rocket might take around 7 months to reach the red planet. An NTR, with its superior efficiency, could cut that time significantly, potentially halving it. Faster travel times aren't just about convenience. They reduce the exposure of astronauts to cosmic radiation and the physical toll of prolonged space travel. Moreover, shorter journeys mean missions can be planned more flexibly, with tighter launch windows and reduced risk of delays due to unforeseen circumstances. The speed and efficiency of NTRs make them a compelling option for deep space exploration. Safety is often a concern when discussing nuclear technology, and rightly so. However, NTRs are designed with multiple fail-safes to prevent accidents. The reactor is only activated once the spacecraft has reached a safe distance from Earth, minimizing risks during launch. Additionally, the propellant used, hydrogen, is non-toxic and poses no environmental hazards. The reactor itself is shielded to prevent radiation leakage, and the design ensures that even in the event of a malfunction, the likelihood of a catastrophic event is extremely low. The focus on safety is paramount, as the goal is to make nuclear propulsion a viable, reliable option for commercial space travel. The commercialization of nuclear propulsion hinges on overcoming several challenges. One of the primary hurdles is the development of a reliable, safe, and efficient reactor that can withstand the rigors of space travel. Extensive testing and validation are required to ensure that the technology is robust and can operate flawlessly in the harsh environment of space. Another challenge is the regulatory framework. The use of nuclear technology is heavily regulated, and new guidelines may need to be established to accommodate the unique aspects of space-based nuclear propulsion. Collaboration between space agencies, private companies, and regulatory bodies will be crucial in navigating these complexities. The economic viability of nuclear propulsion is also a significant factor. While the initial investment in developing and deploying NTRs is substantial, the long-term benefits could outweigh the costs. Faster travel times and increased payload capacity can make missions more cost-effective in the long run. Additionally, the technology could open up new opportunities for commercial space ventures, such as asteroid mining and space tourism. The key is to demonstrate the economic advantages of nuclear propulsion to attract investment and support from both public and private sectors. As the technology matures and becomes more widely accepted, the path to commercialization will become clearer. Government and private sector collaboration. Nuclear thermal rockets, NTRs, represent a significant leap forward in propulsion technology, promising to revolutionize deep space travel. These engines work by heating a propellant, typically hydrogen, to extremely high temperatures using a nuclear reactor. The heated propellant is then expelled through a nozzle, generating thrust. This process is far more efficient than chemical rockets, which rely on the combustion of fuels like liquid hydrogen and oxygen. The higher efficiency stems from the fact that nuclear reactions release vastly more energy per unit of mass compared to chemical reactions. This allows NTRs to achieve higher exhaust velocities, translating into greater speeds and reduced travel times. The collaboration between government agencies and private sector companies is crucial for advancing nuclear propulsion technology. Government entities, such as NASA and the Department of Energy in the United States, provide funding, regulatory oversight, and technical expertise. They often initiate and manage large-scale projects that require significant investment and long-term commitment. For instance, NASA's Kilo Power project, which aims to develop small nuclear reactors for space exploration, exemplifies this approach. Private companies, on the other hand, bring innovation, flexibility, and cost efficiency to the table. Firms like SpaceX and Blue Origin have demonstrated the ability to develop cutting-edge technologies rapidly and at lower costs than traditional government contracts. Safety is a paramount concern in the development and deployment of nuclear thermal rockets. The use of nuclear materials necessitates stringent safety protocols to protect both the crew and the environment. Governments play a vital role in establishing and enforcing these safety standards. They conduct rigorous testing and certification processes to ensure that nuclear propulsion systems meet all regulatory requirements. Private companies, meanwhile, invest in research and development to enhance safety features and implement advanced technologies. For example, they may develop shielding materials that reduce radiation exposure or design fail-safe mechanisms that prevent accidents. The synergy between government oversight and private innovation ensures that nuclear propulsion systems are both safe and effective. The speed advantages of nuclear thermal rockets are substantial. Chemical rockets, which are currently the standard for space travel, have specific impulses, a measure of efficiency, typically ranging from 300 to 450 seconds. In contrast, NTRs can achieve specific impulses of up to 900 seconds or more. This means that NTRs can reach higher velocities more quickly, significantly reducing travel times. For instance, a mission to Mars using chemical propulsion might take around 7 months, while an NTR-powered spacecraft could potentially make the journey in just a few months. This reduction in travel time not only makes deep space exploration more feasible, but also enhances the safety and well-being of astronauts by minimizing their exposure to the harsh conditions of space. The timeline for nuclear propulsion development. Nuclear thermal rockets, NTRs, operate on a principle that's both elegant and powerful. They use a nuclear reactor to heat a propellant, typically hydrogen, to extremely high temperatures. This heated propellant is then expelled through a nozzle to generate thrust. The key advantage here is efficiency. Chemical rockets convert a small percentage of their fuel's energy into thrust, but NTRs can tap into the vast energy released by nuclear fission, making them significantly more efficient. This translates to higher speeds and shorter travel times, a game-changer for deep space exploration. Consider a mission to Mars. A chemical rocket might take around 7 months to reach the red planet. An NTR, with its higher exhaust velocity, could cut that time in half. This isn't just about convenience. Shorter travel times reduce the exposure of astronauts to cosmic radiation and the physiological effects of prolonged spaceflight. Moreover, the increased efficiency of NTRs means less fuel is needed for the same journey, allowing for larger payloads or more flexible mission designs. For instance, a spacecraft could carry more scientific equipment or supplies, enhancing the mission's overall productivity. Safety is often a concern when discussing nuclear technology, but NTRs are designed with multiple fail-safes. The reactor doesn't reach criticality until the spacecraft is already in space, minimizing risks during launch. Additionally, the use of low-enriched uranium reduces proliferation concerns. The spacecraft's trajectory is also carefully planned to ensure that, in the unlikely event of an accident, any radioactive material would either burn up in the atmosphere or be directed away from populated areas. These precautions make NTRs a viable and safe option for future space travel. The development of nuclear propulsion isn't just about speed. It's about opening up new possibilities for exploration. With shorter travel times, we could consider missions to the outer planets and their moons that were previously deemed too time-consuming or fuel-intensive. For example, a journey to Jupiter's moon Europa, a prime candidate for hosting extraterrestrial life, could be significantly shortened. This would allow for more frequent missions and a greater chance of making groundbreaking discoveries. The potential of nuclear propulsion extends beyond our solar system as well. Interstellar travel, once the stuff of science fiction, could become a reality with advanced nuclear propulsion systems. Nuclear propulsion, a catalyst for space industry growth. Nuclear thermal rockets, NTRs, represent a significant leap forward in space propulsion technology. These engines work by heating a propellant, typically hydrogen, to extremely high temperatures using a nuclear fission reactor. The heated propellant is then expelled through a nozzle to generate thrust. This process is far more efficient than chemical rockets, which rely on the combustion of fuel and oxidizer. The high energy density of nuclear reactions allows NTRs to achieve specific impulses, a measure of fuel efficiency, up to 3 times greater than the best chemical rockets. For instance, while the Space Shuttle's main engines had a specific impulse of around 455 seconds, theoretical NTRs can reach specific impulses of 800 to 1,000 seconds. This means that for the same amount of propellant, an NTR can provide significantly more thrust over a longer period. The speed and efficiency of nuclear thermal rockets translate into drastically reduced travel times for deep space missions. A mission to Mars, which typically takes around 7 months using chemical propulsion, could be cut down to about 3 months with an NTR. This reduction in travel time is not just about convenience. It has profound implications for crew health and mission logistics. Longer journeys expose astronauts to higher levels of cosmic radiation and the psychological stresses of prolonged isolation. Faster travel times also reduce the amount of supplies needed, as crews would spend less time in transit. For example, a mission to the outer planets, which can take years with conventional propulsion, could be completed in a fraction of the time, opening up new possibilities for exploration and scientific discovery. Safety is a critical consideration for any space technology, and nuclear thermal rockets are no exception. The primary concern revolves around the handling and containment of radioactive materials. However, modern engineering practices and safety protocols are designed to mitigate these risks. For instance, the reactor core can be designed to operate only after the spacecraft has reached a safe distance from Earth, reducing the risk of accidental radiation exposure. Additionally, the use of low-enriched uranium and advanced shielding materials can minimize the potential for nuclear accidents. The speed advantages of NTRs also enhance safety by reducing the time spent in hazardous environments, such as the Van Allen radiation belts around Earth. While the initial development and deployment of NTRs require careful planning and investment, the long-term benefits for space exploration and industry growth are substantial. The ability to travel faster and more efficiently to distant destinations could catalyze the growth of the space industry, enabling the establishment of off-Earth colonies, the mining of asteroids, and the exploration of the outer solar system. As we wrap up our journey into the future of deep space travel, let's recap the key points we've explored. Nuclear thermal rockets, or NTRs, harness the power of nuclear fission to heat propellants like hydrogen to extreme temperatures, expelling them through a nozzle to generate thrust. This process is significantly more efficient than traditional chemical rockets, offering a higher specific impulse and thus greater fuel efficiency. Imagine traveling to Mars in just 90 days instead of the 7-9 months it would take with conventional chemical propulsion. That's the promise of nuclear thermal rockets. The reduced travel time not only makes deep space missions more feasible, but also minimizes the exposure of astronauts to the harsh radiation of space. Safety is, of course, a paramount concern. While the idea of nuclear propulsion might seem daunting, extensive research and development have shown that these systems can be designed with robust safety measures. The reactor is only activated once the spacecraft has reached a safe distance from Earth, and the design ensures that the nuclear material cannot achieve a critical state until it's deep in space. As we look to the future, the potential of nuclear thermal rockets is undeniable. They could revolutionize our approach to deep space exploration, making missions to Mars and beyond not just dreams, but achievable realities. We stand on the brink of a new era in space travel, and it's an exciting time to be part of this journey. So what's next? Stay tuned for our upcoming series where we'll delve into the cutting-edge technologies that could make interstellar travel a reality. Until then, keep looking up at the stars and dreaming big. The future of space exploration is brighter than ever, and it's powered by the incredible innovations we're uncovering today. Don't forget to like, share, and subscribe for more mind-blowing insights into the cosmos. See you in the next video.